Hello, everyone. My name is Brennan Hill, University of Wisconsin-Madison. Today, I'm presenting our work on the physical basis of prediction, world model formation, and neural organization of LLM-generated curriculum. We explore how world models are formed in biological neural networks, specifically neural organoids, using curriculum generated by large language models. This work intersects with computational neuroscience and agent-based AI, offering a new platform for studying embodied intelligence. I'd like to start with three takeaways of this research. First, we introduce a three-stage curriculum designed specifically for training biological agents. Unlike standard RL agents, biological tissue have unique constraints and the environments of scale and complexity with specific mechanisms like memory and plasticity. Second, there's an automated framework for scaling the training process, designing protocols for biological but were slow and labor intensive. It was moving the human in the loop to an LLM in the loop to handle the experimental design. And finally, by combining these two, we create a high throughput system. By leveraging LLMs to generate increasingly complex environments, we can systematically discover optimal curricula for embodied biological intelligence, moving us from static limitation to true adaptive behavior. Let's look at the physical framework for dealing with embodiment. So we start with a simulation, virtual environment. The environment produces state feedback, which is a stream of information about the world state. We operationalize this feedback through the free energy principle. We treat predictable stimuli, low entropy, consistent signals as a reward. Conversely, we treat unpredictable, chaotic, high entropy stimuli as punishment. This minimizes the agent surprise. The signal is passed the multi-electrode array, or MEA, their physical interface. We designate specific electrode groups for stimulation. Sensory inputs deliver that low entropy reward, or high entropy punishment directly to the tissue. The core processor is the biological neural network. The organoid, as it reacts to the stimulation, record its motor output from separate electrode groups to form real-time neural decoding by comparing spike rates between distinct regions. This decoupling translates biological activity into a discrete action command, like move left or move right, which updates the virtual environment, closing the loop. The cycle allows the organoid to interact with the simulation in real time. So how does learning actually happen? When the agent acts correctly, we deliver a predictable stimulus. This low entropy signal minimizes surprise. Biologically, we hypothesize this induces a long-term potentiation. It confirms the agent's internal model of the world. However, when the agent fails, we deliver an unpredictable stimulus, essentially white noise. This high entropy signal presents a model violation. This serves as an error signal, potentially inducing long-term depression to weaken the synaptic connections that led to the failure. This binary feedback mechanism aligns biological imperative to minimize metabolic costs and surprise with our task goals. A major advantage of this substrate is that we can measure the physical implementation of our world model. We don't simply look at the win rate. Instead, we look at electrophysiology, measuring FE-SPS to detect the actual LTP and LT6 synapses. We can also use calcium indicators to track the formation of stable neural ensembles. And we can perform molecular analysis for post-hoc staining to visualize receptor density changes. We propose a curriculum of three environments to test this. Environment 1 is conditional avoidance. It's a static 1D task. The agent must learn to stay in a safe zone and avoid an adverse zone. The simplest task of state action contingency associates a specific spatial location, encoded via simulation, with negative feedback. Environment 2 is a predator-prey scenario. This introduces goal-directed behavior. The agent, or the predator in purple, must actively navigate to intercept a moving target, the prey in yellow. This increases complexity because we separate the sensory channels. One group from electrodes. One group of electrodes encodes the prey's location, another encodes the predator's location. The organoid must integrate these two data streams. Environment 3 is Pong. It's a dynamic interception task. It requires continuous time control and physics prediction. We use a multimodal encoding here. False exposition is spatially encoded, while the y distance is rate encoded. Tests the network's ability to predict model trajectories. To scale this research, we cannot manually tune every parameter. Instead, we introduce automated curriculum generation. We start with a central data set of logs and the physiological states. We feed this historical data into an automated prompt engineering module. We formulate a prompt that includes the current state of the organoid and the experimental objective. This prompt is sent to a large language model. The LLM acts as a meta-controller. It designs the experiment. The LLM generates the actual Python script or JSON parameters for the training block. It might decide to increase the punishment amplitude or change the stimulation frequency based on previous performance. Crucially, pass through a safety and syntax check. We validate the code to ensure it doesn't violate safety constraints for the biological tissue. Finally, the valid protocol is executed on the MEA platform. The results, neural data, and task performance are fed back into the dataset in a closed-loop system for autonomous scientific discovery. This allows the system to evolve the curriculum alongside the organized learning process. In conclusion, we've presented a framework that treats neural organoids as embodied agents, combining scalable virtual environments with LLM-driven automation create a powerful platform to explore the fundamental physiological connection between environment, embodiment, and intelligence. Thank you for your time. You scan the QR code for the full paper.